Hi there. So today we're looking at monitoring changes in the cryosphere. This is really important because it allows us to see what impact um, the enhanced greenhouse effect is having due to and that resulting in climate change, global climate change, on the ice sheets and cryosphere. This is particularly difficult because they are often remote or inaccessible or hostile environments because they're blooming cold and windy and what have you, or the top of a mountain or in the South Pole, which is not very easy to get to. And also the information we want to know, especially, is things like depth of ice, and that's hidden from us. So depth of ice and its change is a hidden bit of information. So we need quite advanced technical methods of establishing this bit of information. So today what we're going to look at is seismic surveys, radar surveys, gravimetry, and laser or LiDAR surveys. And we're going to look at the different ways in which this is done. So land-based surveys, aeroplane-based surveys, and satellite surveys. So our first one we're going to look at is seismic surveys. This is a land-based survey. So we have the top of our ice sheet. Here we go. So this is the ice surface. And underneath we have like whatever the land surface. So this is all made of rock. And above it we have ice it's like compacted layers of snow, one on top of the other. So this is very dense material, and the ice is less dense. What we can do is place either a device, or back in the day it used to be explosives, and this is called a thumper, and it just puts a big vibration into the ground. And scattered around it at different distances, we will have receivers. And these receivers will record the vibration when it reaches them. So the thumper makes a bang and sends out a pulse of seismic energy. So this is a vibration passing through the material. When it hits a change in density, it will be reflected, and that and that reflected signal is recorded by the receivers. So the closer it is, the sooner the signal bounces back. The further away, the longer it takes for that signal to return to the receiver, and you will end up with a sort of reading that shows the boundary between different densities of material, and that will give you the depth of ice. So you'll be able to work out the ice depth by subtracting it from the rock to the surface. And this has to be done on the surface, so you need some people doing this. You can't do it from an aeroplane or anything like that. Next one is a radar survey. So the way that this works is you can have either an aeroplane or a satellite even. So this is our land, which is this high density rock. Over which is our ice. Ooh, there we go. This is our ice surface. And we want to know what the depth of the ice is. Well, there's two bits of information we need to do. Let's say it's from our aeroplane in this instance. And it will have an altimeter on it, you sending out typically microwave radar. So the microwave is the wavelength part of the spectrum that it uses. And you'll get a return from the surface of the ice, which will tell you the height between the aeroplane and the ice surface. And you can get ice penetrating radars that will go into the ice, through the ice, and then send a signal back to the aeroplane from that rock underneath it. So it'll go through, and so you from, oh, that's not very helpful because it shows a different point. There we go. So we can subtract 1 or A from B, and that will give us our depth of ice. And that can be done from aeroplanes or satellites up in space. Okay. Next one is gravimetry. So gravimetry is the measurement of changes in the Earth's gravitational field. So the way that this works is we have the Earth's crust, which is fairly uniform amount of gravity. So the force of gravity pulling things down is roughly the same. Where we have a large body of something on top of it, like ice. So this is our ice cap or ice sheet. This will therefore increase the amount of matter in that location on the Earth's surface, and that will very slightly increase the pull of the Earth's gravitational field. And that can be recorded in a number of different ways. It can be recorded directly or indirectly. And so that's gives you a measurement of the amount of ice. Or it's also used for things like water in aquifers under the ground. Just like changes in density of the Earth's surface, basically. And the next one then is laser and LiDAR surveys. Again, this is typically done from aeroplanes or satellites. So here's my aeroplane. Obviously a satellite would be much, much higher than this, but I wouldn't be able to fit it in. And this works similar to the radar, except it can't penetrate the ice. All it can do is measure the surface of the ice. It can't penetrate the ice. And it's a very tightly focused beam of light energy. So it's either a laser or a spread of lasers. And then it records how long it takes for that energy to be reflected from a surface and then return up. So a laser is focus light, and LiDAR stands for light direction and range. Okay. You see LiDAR being used more and more for like autonomous cars and stuff like that, and drones have LiDAR sensors because they're cheaper and less disruptive to the electromagnetic spectrum to use than a radar system, which is what used to be done a lot of. So this is really good for telling how the surface height has changed. So as like an ice cap melts and perhaps recedes, the plane flying at the same altitude would find that it takes longer for the beam of light to reach its surface and then return to it, and that would show that the ice has got thinner.